So weighted policy gradients, they work pretty well. They definitely have a couple of limitations. And there's basically this whole other like slightly different way in order to be able to actually get and or optimize a policy. It's all based on kind of like queue networks or the idea for bandits. So then what are these things? So we'll talk about bandits briefly for a bit to get the idea, then queue learning, and then we'll spend a lot of time talking about the ugliness of deep queue learning. Like it works well, but being able to scale it up and getting it to function is a little bit more tricky than we'd hope. Okay, so nothing necessarily new here. Still our favorite RL objective of being able to find, the best action to be able to take. In this case, we're talking about bandits. Um, how many people are familiar with bandits from before? A little bit? Okay, so a bandit is like a really, really simplified agent. So there's really no state. It's just trying to figure out, okay, does anyone know what a bandit is? Does anyone play like slot machines at casinos often? No? Probably better off spending your like money on food. But yeah, so a bandit is like an old term too for slot machines. So the idea is that there's maybe a couple of arms on the slot machine. You're trying to figure out which one of these arms gives you the best like return on sticking coins into this machine. But then we can basically take this concept pretty far in order to actually be able to train a policy. Okay, so this is the idea where we've got this like multi-armed bandit. So there's really at the moment no notion of state, which means, it's kind of like one of those open loop policies. You can take actions or the agent can take actions, but it doesn't have any input. So it's sort of like, it's almost like you can either think of it as there's no state or it's always in the exact same state, the same idea. This needs to figure out what is the best action to take. What is the best like arm to pull on the slot machine? It's also really helpful for analysis because when we get into RL, everything always gets more complicated. But at least in this case, let's start talking about this problem in a bit more detail. And it's this challenge of being able to figure out, okay, should the agent explore or should it exploit? So if kind of think of this problem, which is a little bit probably more familiar to people rather than this kind of like playing the slot machine at a casino. But the robot here is made it to this particular spot and it can either go to one of these two things. It's either like the usual place. And by this is kind of the concept of like, it's tried the arms a couple of different times. It's found one that's currently the best. And the agent can always just choose, let's just go do that. I don't want to bother trying anything new today. It's been a long day. I'm tired of trying anything new. I just want that same like home cooked meal or whatever that I'm used to that gets me through the day. Or it can try something new. Maybe it's the robot has gotten a bit tired of that stuff. Maybe there's an option for being able to find its new favorite restaurant, but it needs to somewhat actively think of these choices. Like when an action is taken, is this an exploit action for using and choosing the action that seems the best, or is it going to try something new because it optimistically might think there's a chance that one of these other things is better? Okay, and now we can formalize this a little bit better. So this is often about regret, which is a little bit different than reward. So regret here is the number of times, you can think of it as like the number of restaurants the robot needs to try before it finds its favorite restaurant. So ideally, perfect world, we like arrive in Montreal or whatever, we walk right into the best restaurant here and like, great, done. Don't need to exploit anything else in our entire existence. Found the best thing. But that rarely happens, especially when it comes to deep learning. So then how can we like balance these two objectives? So each arm here represents some action. So here it's just like a queue function, but without a state. And it's the expectation of like what reward will be received at that particular action. So I've kind of covered that. And then this is where, like, this is the probability distribution that the agent has effectively like learned so far. So action or machine number 2 seems to be the best one to go and try in order to be able to win or whatever, or it's the best restaurant that the agent has visited so far. So it just has like this kind of simple probability distribution. And this is where just getting down to some of the details. So the agent wants to then optimize a policy, sort of similar to what we talked about from before, figure out what is the best action to take, that gets the highest actual Q value. So the number of mistakes then is just sort of like the number of times the agent ends up taking, like the non-optimal action before it kind of decides, okay, this is the best action. So it's probably things that you've been through before. All right. So we're going to think about so then how can we end up coming up with a method that'll kind of minimize this regret? So it'll learn how to take that best action. And the next couple of slides, then we'll kind of expand on this for well, then how can we make a whole policy out of this that can choose actual actions? So one of the ways to be able to ensure to be able to do some exploration and still always be able to find the optimal action in this case. So one of them is epsilon-greedy exploration. This is a somewhat starter way to start to think about doing exploration, but basically add a little small minimum probability of selecting any action at random. So don't always exploit this distribution. And one way to not always exploit this is just with some probability, choose one of these other three or really any of these at random rather than always following what seemingly looks like the best right now. And this is basically what epsilon-greedy exploration is used for. So you'll probably go through a lot of, if you look into Q-learning algorithms, a lot of them by default are going to use epsilon-greedy exploration for the way they end up doing exploration in the actual environment. And if you look at the distribution, basically what this does is just kind of take the actual distribution for what is currently explaining, things that have high value, and basically just adds a little plus epsilon divided by the number of actions. So now everything gets a little bit more probability it'll end up being selected, at least during the exploration process. Yeah. Still, any questions so far? Still pretty good. All right. So then the next part, this is pretty simple exploration method. Still some guarantees that the optimal policy will be found. And in practice, and what also helps is this probability that a random action is chosen should be annealed over time. You'll also see this in any good RL library. Usually the exploration is going to be slowly reduced over the entire training process. And it really helps RL algorithms converge. Excuse me. Okay, but can we at least do a little bit better than epsilon-greedy exploration? If we thought about this a little bit more in the real world, if there was a whole bunch of machines, are you going to try them all entirely at random? That kind of problem is a little bit contrived, but if you were driving, you don't randomly do turns while you're driving the entire time. Some of these are going to be really terrible ideas. In fact, most of them will be. So there's going to be a lot more structure normally in the way that exploration can be done than just totally picking actions at random. So one of these is called an upper confidence bound, particularly upper confidence bound for trees, just because we're just doing a tree search. But the idea is to figure out, okay, how should the selection for actions be adjusted a little bit? So if we've got this process for well, an agent is driving, should it try some more random actions? One way to be able to weight this and adjust it is essentially adding in a slightly different term here. So here, this can be weighted by how often the action has been selected. So if there's, of all the actions that can possibly be taken, rather than choosing them all at random, you can also now choose the action depending on how often that action has been attempted. So if it has not been attempted often, or it's the least attempted action so far, that one actually gets higher probability. Because the idea is, well, we have less knowledge about that action, so there's maybe a higher possibility that taking that action could be useful. And then once that action is taken, a bit more data is got or received. And then this notion of basically computing how often that action has been taken gets updated, and it'll have a lower probability of being selected next time. So this is just basically like it's a confidence bound over how much information and how likely it can be that some action that hasn't been taken ends up being useful. Okay. And then this is kind of a combination of 2 points. So we still have the Q function from before. So it's still a weighting of actually these two things. So whether or not it seems like a really good action to take, and then kind of plus, or has this action never been taken from before, in order to figure out a balance between those two. And this is sometimes the balance here is a bit tricky. There's definitely some more algorithms that add like some small multipliers here and like try to really get into the details for how to make a slightly tighter upper confidence bound. If you're really interested in that stuff, go ahead and read it. There's like tons of papers beyond this. It's kind of old algorithm. Okay. But this ends up working out pretty well. So if epsilon-greedy is basically this, well, it's also blue. So it's this line here in terms of performance. It works okay. It'll converge. But clearly using some version of this upper confidence bound results in in this case, much less regret. So remember here, we want to actually reduce regret, not reward. So I'm trying to figure out how to flip this graph, because usually more regret is bad. Anyway, what this should be is that the UCB policy ends up basically selecting, the less optimal action less often, because it's basically like a likelihood of either take what seems like the best action or randomly amongst all the other ones. So it's kind of likely that all those other actions end up being not, the optimal action to take. Okay. Greedy. I guess maybe it's this Bayesian UCB part that ends up helping and does a little bit better than just epsilon-greedy on its own. Okay. You see that? Here, is that a bit better? Nope. Okay. But this is like one way now that basically we're now getting into this paradigm where there's some discrete number of actions and the agent has to figure out which one of these to take. Okay. All right, so now we'll make just a few steps. So we've got bandits that we can train, and these bandits don't have any state. So now let's start kind of closing the loop on how these bandits can work. Here, the first step is to be able to make what's called just a contextual multi-armed bandit. So now there's at least some information that the bandit is given, and it should now maybe kind of determine that. So I guess if we're thinking about the multi-armed bandit case, maybe the contextual information is different casinos that the actual robot is in. So now it knows to actually try specific arms at specific casinos because they'll have different distributions, something like that. But this is still just optimizing like immediate reward, not a sequence just yet. And this can still do some exploration where the agent, it still can't always exploit, still has to add some simple noise. So like everything we just talked about still applies to these contextual bandits. It's just now there's a little bit of input that kind of controls the distribution some more. If you want to learn a lot more about this type of stuff, you should go check out Pierre-Luc or Doina's class, or I guess these days also Amir's class. It's probably going to have a lot more details about like bandits, convergence algorithms, getting more theoretical bounds on exploration. So feel free to check out some of those other classes to really get into min regret and the details of these algorithms. We're going to spend a little bit more time in this class in the deep Q learning land where everything is still kind of messy and really almost all theoretical guarantees are totally useless, but we still manage to get things to work. Okay, so this is now we make one more step and this starts to become Q learning. So if we wanted to instead learn a state dependent policy, we need a little bit more information. Basically construct this now action valued function that we've already talked about for a bit, but we haven't talked about how to learn this thing yet. And then from here now we need to be able to figure out how to like choose the best action at this particular state. And then here, remember, now we're going to get back to our original reward objective, which is the like sum of rewards into the future, not just an individual reward. Okay, so you might ask yourself, I hope, even though it's a Wednesday, getting a little bit late in the afternoon, um, why do we want to use this instead of policy gradients? So this is a bit of a reminder, or like policy gradients were okay, but what if, for example, the agent could, or we wanted the agent to be able to learn from what's called offline or off policy data? This is rather than only being able to take updates from data that was generated from that specific version of the policy, be able to use some old data. I mean, I'm sure some of us in here probably like remember times we fell over when we were young or something like that. And we still use that data to remind us not to do that thing again. So this is maybe a conceptually useful, mathematically, hopefully like great, because then we can just use like whatever data is available that is generated from anything can be used here to be able to train this policy. It's a couple of limitations there, but that at least seems like a more useful algorithm. And then what we talked about from before, like basically all of the first half of lecture today, policy gradients are very noisy with a lot of variance. So it takes a lot of data to be able to estimate them. So also not really a great input. And in some ways, learning this Q function kind of gives us a bit more information than a policy. You know, a policy just says, this is what it does here. The Q function is a measure of like, well, actually, how much better is this action than this other action in this state? So in some ways, it actually encodes a lot more information than just the policy does. This is good. So maybe there's some more reusable information inside of this Q function than just what's available inside of a policy. Okay. Does that make sense? Any questions about the pros of being able to use, like build on this and make Q functions? Or at least why we don't like, or why we're not always big fans of policy gradients? No. All right. There's many more, but these are the kind of the three main ones. All right. So that gives us basically this question. If there's some experience available, in this case, like D is just some data set, how can the agent actually end up training this function that describes its Q values? So we can't or we won't use policy gradients here because we're coming up with another paradigm. Instead, what is used is basically this concept of approximate dynamic programming. So how many people remember their like third year algorithms class where maybe you covered dynamic programming? No? Been a little while? Okay, well, brief refresher. It's basically just this idea where, if there is data at a couple of different nodes across this process, so let's say, I think there was a good video for this. Let's see how this works. So if we start to collect data at some of these nodes, we can kind of like propagate this information through this network because we know it's connected. It's kind of dynamic programming, such to the point that once we end up sort of assuming that there's information in each of these nodes, and because we can kind of assume that there's not going to be a change here in a chunk of this network, once we end up figuring out like the shortest path here, then we can still kind of basically you can construct all the information that describes each edge on this network. We know that it kind of is always based on that info, and then we can compute a path through it pretty quickly. It just kind of generates itself. So it's because of this like dynamic programming process. So then kind of what's going to be done here is a similar thing for RL. Once we train this Q function to understand values between states, at the end of this whole training process, it kind of constructs this network of how all these values are connected together. And because, it figures out one, like the reward or Q value from this step, it's already modeled the other Q values for other steps. So it can kind of like dynamically back up this information or perform a type of bootstrapping, depending on like what your favorite term is here. Okay, does that make sense? Okay, it's a nice kind of, it requires an assumption or two, but it's a nice property that allows basically like the construction of this network. Uh-oh. Here. Okay, great. So then in this process, very much like we were talking about from before, where we want to estimate the reward to go. So there's a value function estimate for this, but now we're going to focus on this Q function. And in this case, we're doing machine learning here, which is at least a little bit different than just doing dynamic programming. So we're going to do iterative dynamic programming. It's just in this case, we're kind of like updating the values a little bit at every point on all of those nodes. And then if we're doing this process enough, then basically now we've got all the information for how this graph kind of constructs itself together. If you want to know even more details about these algorithms, you can go read these lovely, very recent papers, which will have a lot of good information about iterative dynamic programming. But let's start with, let's talk about one version of this, but just for like value functions. So we get a little bit of a feel for this for RL. So one way is, so we're at least familiar with what a value function is. It's like the value at this current state. And we want to see, okay, given maybe some recent data that's been collected on rewards, like can we improve the value at this state? So if we wanted to update what is the current like value at this actual state that the policy could achieve, maybe I'll put this up a little bit higher. What can happen is basically, it's kind of like the agent can think, but here it's going to do this max over all the possible actions that can be taken in that state. It'll get the reward for all of those. It can then just kind of compute what is the best reward that could be achieved there. Then basically do an expectation over like the next state for all of those actions. So this basically just means it can compute like what'll be the value for the best action from this state. And then it's going to store that information so it doesn't have to compute that again, and it's going to store it inside of this value function. And that's going to be kind of like the dynamic programming part of computing this stuff, storing it. It's always a little bit more accurate every time it stores this information, and then just do this kind of repeatedly over every state. And remember, it's going to be using information from like other future states. So it's going to be kind of building on itself as it gets good estimates at other states. Okay. And this is basically a starter version of what's called value iteration. You can go check out this more inside of Sutton's Introduction to RL book, Sutton and Bartow's Introduction to RL book. To the point where it basically just becomes these steps as one algorithm. So the agent can collect a bunch of experience using the policy it currently has, go through this process of basically, all right, is it possible to be able to make these updates to the value function such that the value function can be like more accurate and be more optimal? And then from this process, although it's a bit tricky, because now we've got this value function, but what the agent needs is a policy. Now it needs to extract the policy from this value function. So now it has to go do this like argmax again over the like actual reward function and the value function. So it's here, there are these two steps for being able to update the value function. And then from that, kind of like pulling out now the new policy that's best for the agent. Yeah. So there's these two steps, but maybe some people are already starting to notice a bit of an issue with this. At the very least, it's kind of like, well, this seems like a lot of compute, at least. Like having to generate a whole policy from the value function can be pretty costly, especially if this has to be done after like every data point is collected inside of the environment. So this might be like for every data point, at least a number of samples equivalent to like the number of actions from that state needs to be iterated over to see what gets updated. So it gets a bit expensive. The part that's nice though is this still can work well. It's guaranteed to converge to be able to find an optimal policy, even to a stationary policy, even in the infinite horizon case. And like I said, it just acts by, so technically to get the policy, it has to perform this argmax over knowing the reward and over the value function. So every time it gets to a new state, kind of has to sample everything inside of its own model and then get the best action out of that. So a bit costly. But here, and this is just talking about policy iteration a bit more. So this is a little bit different. So instead, try to fit a policy directly from the data. So here, before, this can, like, is done in two steps. Sorry. Okay. for being able to update the actual value iteration part, and then being able to do this for getting the next policy, and then doing this policy improvement step instead for actually being able to get the new like policy at that particular point. So now this is trying to learn more of an actual policy. The previous one was more so like learn a value function, compute the policy at that actual state, like what is the best action. This can then try to like next step encode that into a policy that can be used more. And then these can kind of bootstrap each other a bit. So now the policy in this next step doesn't have to do a whole argmax here. It can use the policy it's got so far, which should already be a representation of what is the best action to take at this particular point. Does that make sense? So like now it doesn't have to do that argmax every time it gets the new state. It kind of relies on its previous policy, which should already have like backed up a model for what is the best action to take at that state. So a little less computation needs to be done here, but it is bootstrapping on itself a little bit. So it's got a little bit of trust in that this policy is still an argmax. So these two will still have to kind of like update each, but together they'll end up finding a good policy that ends up being the best. Just takes some amount of this policy iteration. So these are all learning. Okay. So then the last real kind of step is, okay, I get that there's some policy evaluation and then policy improvement as well. Can we stick this all together into one kind of thing so that we don't have to split this into two steps? And then it can be much faster. Because like maybe as a quick aside, okay, especially for this example that has to do a max overall actions to end up getting the policy. We mentioned for a bit, like how many actions were possible inside of the StarCraft environment. If there's like tens of thousands of actions, this means this needs to run over like tens of thousands of possible actions for each state, which means that's going to take a considerable amount of time in order to be able to do these updates. So it's basically, can we at least figure out how to, pre-compute a lot of the information for the policies and good actions, such that we can save a lot of time, even if the action space starts to grow. Because the problem here is basically this, the learning time and running time depends on the size of the action space or its dimensionality. So the next step is, okay, there's a now a nicer variation on this that's called Q iteration. Here, the previous methods are, like I was saying, impractical for large, also continuous action spaces, because it's really hard to enumerate all of those. And now it can just have to worry about iterating over just the large state space. So here for all states, we can do, or sorry, like this is an example of this process where like value iteration, it does have to do this over all possible states, which can still be kind of expensive. And then it also has to do this over all possible actions. So this is a lot of information to be able to back up, even just to get some information for what is the next value. And then also, because we don't know the dynamics, technically for value iteration, it still needs to do this whole sampling process over the possible dynamics given the actual model. I mean, long story short, this just doesn't really scale well in terms of like action dimensions or state dimensions. To overcome these issues, the variation on this is basically called Q iteration. With a few assumptions, it's just now instead of updating a value, we'll update a Q value that also stores information per action given over the rewards. And there's still the argmax over actions here, but at least there isn't as much like additional iteration over all possible states that needs to be done after every update that's done to this Q function. Okay, does that make sense? Questions? Still pretty good? Okay, this is just basically with a little bit of an assumption here, which is that the Q function in the future will always select the best action, which can sometimes cause some issues we'll talk about. It basically means the algorithm can start to eliminate or like reduce a lot of these other like iteration steps that are all used here. So this just ends up encoding things pretty fast. Technically, this is actually pretty easy to run in a deep network as well, because you can just do like argmax over this vector and get your best action. So it's fairly fast, because this can all still be encoded kind of quickly as like one gradient operation, as long as you get your like indexing right, doing this argmax properly. Okay. So then this Q iteration algorithm. So this is basically, like the textbook version of being able to look at Q iteration. This is how like values are updated for this particular state in action, where you have to be able to figure out what the next best action will be in the next states. But how this is actually done for deep learning is basically we convert this into a loss here. So here we end up constructing some type, and here this is called the temporal difference error. So now it's very similar to that value function error that we had from before. And this is v of s of t plus 1. And then there's a reward in the middle, such that basically the loss is this chunk here is basically the target. And we want our actual Q function to like minimize, like reduce the error between its prediction and what'll be this target. And the target is now the reward plus the Q value at the next state and the assumption that the agent is going to pick the best action that it's at least learned so far. And then this is just over some pile of data. So this is different, at least here. This isn't necessarily over a policy like the previous Q functions, although the idea is this data is still generated from this Q function, but now it can just train over this and be able to minimize what's called TD error or Bellman error. Okay. Does that make more sense than all the other piles of stuff about Q functions and policy iteration? Okay. All right, so then let me just at least cover one of the details that ends up being, well, two of them end up being pretty important. So one, the algorithm isn't too complicated, which is a nice start. Collect some experience using some policy, compute these targets, which is just this part right here. Minimize the parameters for your policy, your Q function here, which is just your Q function minus all of those targets. So basically become better at predicting, like the best Q value that could come out of the actual policy. And then note, at least if you end up coding something like this, make sure you do like a stop gradient on the Y, the target variable here. So you only really want to be minimizing one side of this particular network. Otherwise, you're going to end up with some pretty probably divergent training in this case. So make sure either to use like a stop grad or compute this separately and do a detach or something like that. Okay. But the last part I just want to get to before we end up taking off is a little bit about understanding when and why these converge. So we kind of talked about these like steps. Value iteration ends up updating values, but then how does this end up converging to a policy, like something that we know is a fixed optimal policy? And there's really two things we need to check on. One is that, so this Bellman update is something called a contraction, which you can look into some more details later. But what it really means is that like, the distance after like the Bellman update is performed between, like this is basically the Q function here, and these are the previous values in like the same distance space. So that basically after an update is performed, the distance over the outputs is not larger than the distance over the inputs. So it's like, you can kind of think about it, it's like literally contracting, because we're minimizing the errors between the outputs and those rewards. Over time, this should reduce, with the extra assumption that your reward function has to be bounded. So like if your reward function is infinity, this whole thing explodes. And that's kind of the reason why I'm describing this. It's okay. We need to think about this a bit more when we get into deep learning land. Because if we introduce something into the way our Q function is being performed, and it's possible for it to kind of like break out of this behavior such that now like you do an update and the possible Q values are expanding really quickly, it's going to diverge and explode. And this is what's going to happen a lot in like deep learning, approximate function land. So just keep an eye on this and make sure that the Bellman updates are being performed are still a contraction. And we'll talk about a couple of tricks, I guess, next lecture about how to help make sure this is still a contraction. And if you want to get into some of the details, this is where like this is technically like a version of the contraction description for the Q-learning update. And it's just that, when this Q-learning contractor update is applied to both the Q functions, it ends up being a little bit less than kind of just the original Q values. So everything is shrinking. So then over time, after many, many updates are performed, this thing will converge down to a policy, a single optimal policy that'll be performed, be used. Okay. Any questions about that? No? Yeah. The equation at the bottom. So I think this is actually from, shoot. It's not from the Intro to RL book. It's from, I think it's Casba's small book on reinforcement learning. So yeah, send me a message. I think this is from chapter 4 or chapter 5, where he goes over like contraction operators for Q functions, and some details from there. I think. Oh, yeah. And then I'll also probably go back and add the citation for this that I thought I already included. But keep that in mind. This here is basically what, as we make deep Q learning algorithms, we're going to be battling this repeatedly such that things still converge and learn. And it's at least good to always have this in your mind. I'll refer to it a lot to say like this model was chosen this way because if it was another way, most likely this contraction is not going to be as good. And what's called the Lipschitz constant, which is kind of like this related to this Q value, is like we want that to be smaller. And that means that this thing is becoming a contraction. But we'll talk a little bit more about this in the next class. All right. Any other quick questions? All right, great. Take care, everybody. Hopefully I'll see you all on Friday. Enjoy the weather.